Yeah, welcome everybody. Good to have you here. I'm very grateful to have also my colleagues Thomas and Mathieu here today with me, who will guide you through the demo and share their insights. So what we're going to present today, we talk about real-time streaming and reliable transport. So basically, what we are doing is we really try to keep it short and simple for you guys. We will not talk much about network congestion itself. We will try, or we will talk about how to fix it. And yeah, so that's me. As I said, Thomas and Mathieu from our research and development team will guide you through the presentation and show you the actual demo. Ceeblue, we've been founded in 2017, and we originally started with transcoding solution for OTT and telcos. So that is our specialty also. Still today one of our core markets. And we also have a media fabric, which is our second core product, which is basically a software-defined network fabric with video processing capabilities. We are a true multi-protocol vendor, so we support lots of protocols like SRT, WebRTC. We've been one of the first adopters, or one of the first adopters of WebRTC, and doing specialty like one-to-many WebRTC streaming solutions. Yeah, so network congestion. What is the problem with reliable streaming, right? In reliable streaming, you have no recourse against limited bandwidth. So basically, when you look at ABR, which is already a good technology to have if you're having some sort of limited bandwidth on the customer's network you're trying to stream to, you can reduce the quality to medium quality to low quality, and then your low quality is still above the limited bandwidth, right? And because you're using a reliable protocol, it's important for you to transport every frame, especially like, for example, in a sports game. It's really important to not miss the goal, right? So you really want to use a reliable transport for that. So what happens normally is that if you using reliable transport, is that if you have congestion now, so you're basically on the lowest rendition, you can't go lower, so you cannot reduce your bandwidth of the ABR. Your stream will never catch up, right? This is how reliable transport works. You will have building up a queue, but it's really important to not build up a queue, right? Because what you want to do is actually you want to, in real-time streaming, you want to push your packets as fast as possible to the viewer. And if you're building up a queue, you will have overflow, and this will then trigger retransmits. And then you have like a never-ending story there. You have a downward spiral, which you cannot resolve, right? So what options do we have in that situation, right? A common option, a common option nowadays, people think that it's useful to display a wheel. So that's one option. I think we can... Yeah, I think for us, at least, it's not an option to display a wheel. So what we can do is basically make the reliable transport partially unreliable. So basically, by having a transport layer on top of a transport on top of the transport, which is aware of the whole situation. So what we can then do is we can skip some video frames and prioritize audio, or being really aggressive, skip all data, so all frames, all audio, everything, and just catch up to the live point, right? So, which would then resolve the network congestion, because if you're not putting more data into the pipe, you would resolve then the network congestion and could play up at the real-time point again, right? So another problem currently that we see is that in adaptive bitrate, there's lots of communication going on between the server and the client. So you may rely on a third-party vendor for that also. And it takes too long, right? So if you're waiting for the data from the player, so the player tells the server, well, I don't get any data here. How this would work in a normal situation is that you can continue to play in about, I don't know, like 3 seconds something, or you display the wheel again or something else. And in an already congested network, you will have issues even telling the server that something is wrong on the player side, right? So a better approach would involve something that the player is constantly aware of if there is congestion or not, and the player can independently act upon that too, right? So this is why we investigated basically two different approaches. One is adaptive push and adaptive HTTP. So why we choose that? Because it's widely available, right? So most of the current implementations rely heavily also on CDN support. So one important thing was to really have broad CDN support. And yeah, so Thomas, will you tell us what we did and what WebRTS is?
Yeah, do you hear me? Good. So this is the reason for WebRTS. WebRTS is a web real-time streaming. It's a new library that Ceeblue has developed to make real-time streaming more resilient to network congestion with no compromise on the quality. It is a transport protocol and codec-agnostic. It supports partial reliability. Most important, it supports less than 500 milliseconds end-to-end latency. Sorry. In WebRTS, we defined two strong goals, which are being safe real-time adaptive bitrate, meaning we don't want self-sustaining congestion with the lowest bitrate, and we want to support partial reliability, which means when the lowest rendition is selected, it will not congest, but to stay in sync with the live, it will skip frames, simply. And as I just said, WebRTS is agnostic to transport protocol and media format. And currently, we have implemented HTTP and WebSocket for the transport, but it will be more, and it can be more. For the media format, we support CMAF and RTS, where RTS is our own-made media format, which is, compared to CMAF, it is 5% less bandwidth. Yeah. So let me talk about the first approach we are presenting today under the new WebRTS framework. It is adaptive push. The main idea of adaptive push is that the server determines where byte rates are switched, requiring no interaction from the player. All is done on the server side. And this is an HTTP or WebSocket streaming from the server. And the server changes the tracks in real time according to network conditions, without any interaction on the client side. All the code is on the server side. Here is a sample of pseudocode to understand how it can be implemented. You send the frame in blocking mode, and if the elapsed time is more than the frame duration, you have a congestion. So you have to decide to skip frames or to lower the bit rate, depending on the condition and the possibilities. That's the idea. So let's show an example of this. Yeah. Yep. So you can see, if you can directly open it inside the browser, and it will switch smoothly the rendition going to the highest. Let's try to add some limitation on the byte rate. That's it. Okay, and you see the rendition is the lowest now, and we remove it, and it will turn back to the highest rendition quite fast. So, and all has been done on the server side here. So this is quite promising approach, allowing to play the stream in real time with perfect congestion network resilience in any player. It can be via VLC or directly in the browser. And currently, this approach is restricted to Ceeblue in edge case and edge case. So let's talk about the other approach we implemented. I present you Mathieu, my colleague.
Yes, thanks, Thomas. And hi, everyone. So now we speak about adaptive HTTP. After experimentation on the server side, we try now to explore a more conventional approach with a segmented protocol like HLS or LLHLS or LLLLHLS. It's really, yes. So an HTTP adaptive protocol close to HLS, but with the following improvement. In first point, a predictable sequence pattern. Unlike HLS, this protocol allows to prediction of sequence pattern. There is no need for playlist request, which address common issue with CDN, with CDN caching. In second point, the seamless attachment to the live point. The protocol can attach new playback directly to the live point. This achieved by using a special keyword to request the latest request. Then the server redirects the client to the URL of the last sequence and initiate a progressive download, the check transfer progressive download. And in last point, the support, of course, of the partial reliability transport. The protocol supports partial reliability transfer, enabling the client to skip some sequence if needed to recover live content more efficiently. Let me go to the demonstration. Maybe it's more speaking. Yes, I'll start with the manifest file to describe the stream. It's not really like a playlist file. It's a manifest file, yes, with a stream, all the stream metadata inside, the different video track with different resolution, with different bandwidth. It's just to explain what is the stream. And you see it's identifiable by a number ID, every track, audio track by the number even. But the most important thing is about the sequence pattern. Sequence pattern is very simple finally. Track ID minus sequence ID point extension. I report it inside the URL, and I can replace it by any track ID, for example, one for the video track, And sequence ID, I use the special keyword last and agnostic for the extension. So I can use MPEG-4 for CMAF, of course. And you see, I play just one GOP. It's not a segment, it's just a sequence. And let me do again to see exactly what's happened about the network. It's really an HTTP 307 redirection to the last segment. It's useful for the CDN. You redirect to the correct segment. And after, it's just it finally, because it's intuitive. It's possible to play the following segment just by increasing by 1, 4, 5, etc. And to change finally the rendition, simply change the track. Track 2, for example, track 3 for different rendition, or 11 for the audio, no, 5 for the lower rendition, and 11 for the audio. Okay. Now you understand the basic. It's very simple finally. Now you understand the basic. Let's go to the player integration. The player integration. You see, I play HTTP adaptive. We see different renditions with an automatic adaptive bitrate algorithm. And we display a lot of statistics like buffer, latency. Latency is a bit approximative, but it's interesting for interesting for us. Look, it simply requests one time an index file about metadata, and I request every sequence one by one, 11 for the audio, and every sequence for the video, etc. And no more playlist request, contrary to LLHLS, etc. We have a full control about the buffering. You can set a maximum buffer and minimum buffer, and you see the player reached to get the middle, finally 200 milliseconds, exactly the middle of the buffer. Let me demonstrate the low latency side. I open exactly the same stream on the right side with a WebRTC player, and you see we have something very comparable. It's sometimes a bit better on the left side. If I capture again, maybe, yes, I get something a bit better on the WebRTC side. But yes, it's completely different with HLS. Yes. But maybe the most important is the ability to change the protocol between reliable or not reliable dynamically, so during the streaming. So look, I put the protocol like a reliable protocol with a minimal rendition quality on the left side and on the right side. Now I emulate congestion with a net limiter again on all the browsers finally. So it's impact with the same way the two protocols, WebRTC and WebRTS. And look, we start to get latency from the both sides. WebRTC exactly like WebRTS. But with the time, look, 9 latency, 10 seconds, 8 seconds, 10 seconds, and every time I get a gap because the buffer is empty, we increase the latency because it's a reliable protocol. Now I remove the limitation, and you see WebRTC is able to recover the live endpoint automatically. And on the left side, no, because we have a reliable protocol. So 11 seconds of latency. I search to, no, yes. No, I uncheck reliable, and immediately we recover the live endpoint exactly like WebRTC, because finally we have switched it dynamically from a reliable protocol to the partial protocol. We have built finally an unreliable protocol support on the top of transport reliable. It's really the reason, no, because we have met a lot of problems with, no. We are very happy about WebRTC, excepting about some points like artifacts, because we don't control the random packet lost. So sometimes we get artifacts, and it's not compatible with CDN. And on the left side, yeah, so we don't want to reinvent the wheel, but we share something very simple, finally, to fix some things over HTTP protocol. So, finally, we have something over HTTP with network congestion resilience, real-time latency, compatibility with standard CDN, a very simple implementation with a predictable pattern. It's stable because it's close to HLS. Yes, it's really stable. And just require 2 HTTP channels. It's something maybe resolved by HTTP2 because we have needs of 1 channel for audio, 1 channel for video to be compatible with different combination of rendition between video and audio. Thanks for your attention. I pass the speak to Jonas for the conclusion.
Yeah, so to sum this all up, we basically created a framework completely from scratch for this. With basically all the knowledge that we gained from all the implementations we did with all the other protocols. And we really try to build something, or we built something that has all the benefits of reliable transport with the ability to being partially reliable when it matters, right? Because what we really wanted to create is something very similar with sub 500 millisecond latency to WebRTC, but with the benefits of being also reliable. Yeah, so basically we already achieved lots of milestones, which is the first implementation based on reliable transport. We will also already working on UDP-based transport. So WebTransport HTTP is something we are actively looking into. We are also following MoQ very closely, what's going on there. Yeah, and also we have a couple of things why we were developing this. Also ideas about moving the forward error correction to the codec, basically by using SVC. So the protocol allows also for headers that are custom to make this basically happen. Yeah, and we are also looking forward to integrate web codecs to be a little bit more like open to new codecs, because nobody knows what will be the next codec to use. I mean, AV1 is obviously on the rise, but there are so many evolvements also, especially in restoring frames if they are partial, if you have partial loss on the frame side, not to skip the frames, but maybe to morph frames or even restore frames based on the capabilities of the device. Yeah, so thank you very much. If you want to try it out, you can try it out. Scan that. If you want to have like a personal demo at our booth, you're welcome. We can do an in-depth talk and show you all the details. And we also having a little happy hour over there. So also, if you just want to grab a beer, you're very welcome to join us. Yeah, thank you all for attending. And if you have any questions.